It's my pleasure to introduce today's colloquium speaker, Max Krohn from MIT. Max is also a faculty candidate. Max has been doing work with Franz Kaschuk at MIT, as well as some other collaborators, Robert Morris, Eddie Kohler, and some with David Maziras. And prior to MIT, Max got his bachelor's at Harvard with Mike Mitzenmacher and Mike Rabin as well. For those of you who want something non-academic to talk about with Max, you can ask him about the two companies that he's co-founded that seem to be thriving as well. So with that, Max, take it away.
Thanks, Steve, and thanks for having me here today. So depending on who you ask, people might say that there's a computing shift going on now. But for the last 20 years or so, we've been using the PCs in our office to both store files and run all sorts of interesting computations on those files. But of course, as we all become more interesting uploading our important data onto web servers, we're also now beginning to run applications on that data on the web servers using code that actually runs on the web servers themselves. So if you ask somebody like Google, they'll say in a couple of years we'll all be using Google Spreadsheet rather than Microsoft Excel. And other players like Facebook are trying to get in on this type of trend as well. So given the way that computing might be shifting from a desktop-based model to more of a server or cloud-based model, what are the important security implications to keep in mind? Well, first of all, it's important to realize that all these fancy new web services are just supersets of the old. And as such, they're susceptible to all the same types of attacks that we've been seeing for at least the past 10 years. And here's the first one to think about. It's what I call the classic attack. So in this case, imagine there's some bad guy, Bob, and what he really wants to do is get access to some secret data that this web application is trying to keep from him. So in this case, Alice and Bob both store data on the server. So what's Bob going to do? He's not going to just click on links as he's supposed to, but rather he's going to formulate some very unexpected request to this web application, which is going to trigger some bug somewhere in this code that Bob found out about. And lo and behold, this application is now going to suck data into it that's not actually Bob's. It belongs to Alice. And then it's willing to send that data back over the web to Bob. And of course, once Bob figures out how to do this, he could do it for all sorts of other people who also store their data on the server, for people like Chuck and Doug. And before you know it, he has the contents of the whole server-side database. So as you know, this is not an academic concern. If you read the popular press, this shows up all the time. And it's pretty embarrassing when you're a university or a corporation and your files get broken into. And it actually probably makes people's lives actually pretty miserable. So this is not something you want to happen to your web company or university. And as much as possible, you'd like to avoid it. So this is what I call the classic attack, the type of thing we've been seeing for the last 10 years. But what's going to happen as these websites get more interesting? And here's an example where I'm going to use Facebook, because they seem to be on more or less the cutting edge of these web technologies. So here's what Facebook looked like about 3 or 4 years ago. Alice would show up to Facebook. She'd say, Facebook, please show me something like feature A. And in this case, she trusted that the Facebook developers actually did a pretty good job of implementing feature A, and so that maybe she would only be able to see her data, not Bob's data, if Bob didn't want to show her his data. But as of about a year ago, Facebook did something quite innovative. They said, well, we're tired of running all these applications ourselves. Why not open the process up to these third-party application providers? And so now when Alice goes to Facebook and asks for feature C, what's really happening is Facebook's taking that request and sending it over the internet to some third-party web server administrated by some entirely independent corporation. And now feature C is going to access Alice's data on the server as it responds to Alice's request, and eventually send the data back to Alice. So of course, if Bob is the guy who's actually writing this application, what he'll do is he'll set this third-party server up as just a way to collect Alice's data and eventually ship it off to his machine to do something bad with it. So in this case, Facebook has managed to provision this sort of server-side malware model in which Alice can mistakenly use software that's not really acting in your best interest. So it seems like things are going from bad to worse, that we always had this web security problem, this classic attack that I described. And as websites get more interesting, we're seeing the possibility of server-side malware. And of course, there are lots of other interesting attacks to consider, things like cross-site scripting or phishing. And I'm not going to get into those today, but obviously they're extremely important problems that demand attention as well. But from here, it seems like our body of web users have two more or less options at their disposal. They can just say the web is getting too complicated and I'm not going to, and therefore it's best to disconnect and potentially retreat into underground bunkers and disconnect entirely from the internet. However, there's a flip side of looking at this, and that is if we're now changing the way we do our computation, this might actually be a great opportunity to build systems from scratch that have the right security properties built in. And we're going to go after the second way of looking at the new computing shift going on with web services. So this has been my work mainly in graduate school. And as Steve mentioned, I started actually in more of a commercial way of looking at these problems, in which I actually was in charge of making sure that websites were not losing their important data to attackers. And as I got to grad school, I started trying to apply some of the lessons I'd learned into into a more general context that would be applicable to different websites. And so what we'll be talking about today is the two last works on this slide, one of which is about building a new web operating system for making web applications more secure. And the second is about how to potentially build future websites like the Facebook site we've seen before. And before we get into those specific works, it's useful to ask ourselves now why this problem is so difficult, to zoom in a little bit and see what it actually is we're talking about here. So here's my schematic diagram as to what a website looks like. And you can imagine there's some off-the-shelf storage engine like a database or file system. And then maybe there's some off-the-shelf web server like Apache that's speaking to clients. But in the middle is where all the action is. And this is the stuff that each individual website has to do for themselves and get right in order to both do their application and also be secure. And so we can ask ourselves now, what happens if anywhere inside this big mess of stuff running on the server, and as you can see in this case, it's maybe in different languages and different address spaces. It's a pretty complicated system. But what happens if there's a bug anywhere in one of these different components? And in some cases, a bug is equivalent to some sort of security vulnerability, assuming an attacker is going to take advantage of it. And also, if you're thinking about Facebook, now you have to ask yourself, what happens if you put the bad code directly in this blob of stuff that needs to be correct in order for a website to do its job and be secure? So as much as possible today in our talk, we're going to be treating this complicated mass of stuff running on the server as a black box and not have to worry about it in terms of security. And so how might this work in practice? Well, some storage engine, so some code inside the black box is going to respond to an incoming web request. And it's going to pull some file like Alice's data off the storage engine. And after that, there's going to be some automated mechanism, perhaps implemented by a compiler or an operating system, in which the data is tracked as it moves through that black box. At the end of the day, that data is going to be spit out the other end and towards the internet, but only after it goes through this little red piece of code called a gateway. And what the gateway is a place on our system where we're going to hope to concentrate all the important security logic. So therefore, if we want to audit this system, we really focus our efforts on the gateway. Don't really have to worry about what's going on inside the black box. So the real question here is how to actually implement the type of data tracking I described inside the black box. In particular, are we talking about runtime or compile time tracking? And in my experience, I think that websites actually do favor a form of runtime tracking. That a lot of times they're built with scripting languages, things like PHP, Python, and Ruby, things that are not statically analyzable in terms of any sort of type guarantees. And also there's this trend towards mixing and matching different languages and different technologies, basically duct tape whatever it takes to get a website working. And finally, there's also a desire to plug in all sorts of third-party and plug-in software. So I think if you add these three things up, it'll be pretty hard to fit this all in a framework in which one compiler can statically analyze everything. So the idea that we're going to be developing in general here is one that's called Decentralized Information Flow Control for the operating system. And it's really what I've been talking about. It's analyzing what's going on in terms of the black box at runtime at the OS level, and then pushing all the important security decisions to one isolated piece of code. This is the general security plan we're going to be describing. As I've mentioned in the slide, this is actually influenced by existing work in the PL community that dates back to the late 90s. But we're seeing it here at the OS level for the first time. So the contributions in my work that I want to that I'm going to hit on is first and foremost this idea of end-to-end web security, of trying to take our websites today and factor out the security guarantees so that most of the website can be seen as a black box. To realize these ideas, we've actually had to invent some new technologies. So the important one that I described is first building websites with decentralized information flow control. And part of that was trying to get the right model for the way this is going to work at the OS level, figuring out what the API should be for applications, and also a case study on a real web application, and also an implementation on a real OS as well. And hopefully at the end of the talk, we'll have time to generalize these ideas to see how they can apply to extensible websites that are going to be the norm in the future. And in the outline, we're just going to hit all three of these points in order, and starting at first with what it looks like for operating system support for DIFC. So here's a general framework that we're going to be talking about. Imagine some website, and it's now split into two separate pieces. One of which is the web application, the part of the code that's actually doing the interesting work that this website's going to do. And the other is some gateway that's going to be in charge mostly of security. And also, in my example, I have a new kernel, not just a regular off-the-shelf kernel, but something that's been modified to enforce DIFC guarantees, information flow control guarantees. And finally, there are two different files, Alice's file and Bob's file. And now there are labels beneath them by which the OS knows exactly whose data this is. And here's what an example looks like when Alice tries to get her data out. So Alice's data is labeled as Alice's data. And when the web application pulls that off the file system and tries to do something interesting with it, the underlying kernel makes a note of the fact that the application read that file. Then it does some sort of transformation to it and sends it back out to the gateway, which is going to implement some type of policy. In particular, only send this data to Alice and not to Bob. So that's really the primitives we need. And as I tell you how I'm going to describe it, I'm going to do it in terms of what's here. So first and foremost, I need to show you, well, just first, I need to show you how to label secret data. So there's Alice's data, there's Bob's data. What other types of data is there? Second, I want to tell you about how the kernel is able to implement this data tracking, in which it knows that the web application read the data. And third, there's this other last component about how an application like the gateway is able to legislate some security policy that makes sense for this application. And you could think about this as a split between some sort of enforcement, in which case the kernel is doing the enforcement, and some legislation of security policies that the gateway is going to do in application space. And so we'll hit these 3 points in order. So the first point is how to label data. And the way our system is going to work is that each file or process on the system is going to be given a secrecy label. What a secrecy label is just a conservative summary of all the secrets that have influenced that particular process or file. So certain examples include, well, this file contains all sorts of secrets about Alice, or maybe this process contains something like financial secrets, or maybe this process contains both Alice's secrets and financial secrets. So in our nomenclature, we're calling these individual components tags, and arbitrary sets of these are called labels. And each process or file in the system has what's called a label. OK, the next idea is how data is actually tracked. And this is actually implementable with two simple rules. The first is going to be when processes are allowed to speak to the network. And the rule for that is that a process can only speak to the network if so doing won't spill the beans about any important secrets. So to translate, a process P can only speak to the network if its secrecy label is empty. It hasn't seen any secrets. But the other thing about the system is to determine how secrets can flow inside. And so you can imagine two different processes, P and Q. And there's going to be a rule, and information can flow from P to Q if P's secrecy label is a subset of Q's. And let me show you in practice why this seems like it makes sense. So first imagine a web application and a file. So just consider a file as just pretty dumb processes. But in this case, a web application has seen Alice and Bob's data. So it's labeled A for Alice, B for Bob. And some file has the label A on it, A for Alice. And so what does the subset rule mean in both directions? Well, it means, first of all, this web application should be able to read the file. Because in reading the file, there's nothing that the web application can learn that it doesn't already know itself. So the kernel is going to allow the read in that direction. The other thing is that the web application should not be allowed to write data back to that file. The kernel will deny that right. Because if it were to allow it, it would allow this web application to scroll information about Bob's data into this file as this label for Alice. And you can apply the same type of subset rule in other cases to see, well, yeah, there's some helper process P in some web application, and they're labeled with incomparable labels, and therefore information shouldn't be allowed to flow in either direction. So this is just the subset rule showing you, shown through a bunch of different examples. OK, so I've showed you how to label data, how to track data. The last thing I need to talk about is how this overall policy about how Alice and Bob can access their data is actually legislated at the application level. And for this, there are 3 separate rules I need to describe. The first is that processes are allowed to change their labels by adding tags, and any process on the system can add any tag it wants to its label. The second is that processes can allocate new tags, and the third is that some processes can subtract tags. And let me show you in practice why this makes sense. So the first thing to go into is any process can add any tag, as I've described it. So something like a web application, when it first boots up, it'll have an empty label. But then it'll say to the kernel, well, I really want to see Bob's data, so please change my label from being empty to having B in it, B for Bob. And the kernel will say, sure, I'll let you do that. But if it later changes its mind and tries to actually remove that tag from its label, the kernel will say, no, I'm not going to let that happen. So in this sense, changing label can be a one-way operation. So that's just adding with tags. So web applications or any applications can add any tag they want to their labels. The next question is where these tags actually come from in the first place. And for a good example of this, consider what happens when Alice logs onto this website for the first time. So when she's introducing herself to the gateway, maybe filling in some kind of form describing her email address and how old she is or whatever, the gateway will say, well, I need a new tag that corresponds to Alice and Alice's secret data. So in our system, we allow processes like the gateway or any other process on the system, for that matter, to create new tags. And in this case, the gateway created a new tag. The kernel gave it back something that looked like a random 64-bit identifier. And then the gateway associates that identifier with Alice in its mind. As a result, there's this important side effect that I'm showing on the slide. And that is, we've now updated our model a little bit to say that each process has 2 different labels, an S label for secrecy, a D label for declassify. And as a result of creating this new tag for Alice, the gateway gets a new tag put into its declassify label, A for Alice. What does this mean? Well, imagine the gateway does something like any other process on the system where it says, my secrecy label started out as empty. Please, kernel, change my secrecy label to have A in it. And the kernel will say, sure, that's fine. But now what this gateway process can do is it can actually subtract that tag back out of its label and ask the kernel to change it back to empty. In which case, the kernel will say, sure, I'm allowing you to do that because you have the ability to declassify this tag A. So given these 3 different components of how the system works, I'm now able to show you how we could actually get real security properties and web applications out of it. So the first thing to consider is what happens when Alice tries to get her data back off the system. And before this picture ever happened, Alice and Bob both signed up for this website, and therefore the gateway has the ability to declassify both their tags. So its declassify label says A and B in it. And note the web application has an empty declassify label, meaning it doesn't really have any important privileges. So what happens when Alice tries to read her file back off the file system and asks the server for her data back? Well, the first thing that happens is the web application and the gateway both change their labels from being empty before to having A in it now. And because any process can add any tag it wants to its label, the kernel will say, sure, that's fine with me. Now one can apply the subset rule to see that, first of all, the web application can read the file in the first place off the file system. Once it has the file, the web application can do any sorts of interesting transformations it wants. It'll do whatever interesting things this website is in charge of. And then it'll, at the end of the day, try to send that information back out to Alice's browser. The first stop along the way is this gateway process, which again can receive the information from the web application just because of the subset rule. And finally, once the gateway has this information, it can now change its label to being empty because it has the explicit ability to declassify that information, and then can send data back out to Alice. It also could send data to Bob if it wanted to, but whoever installed this application is trusting the gateway to just send that data to Alice and not to Bob. So there's the policy that this gateway is able to legislate. So that was Alice trying to get her data off of the system. What happens when somebody like Bob tries to attack the system and try to get Alice's data out when you shouldn't be able to see it? So let's make the pessimal assumption that there's some bug in this application, and Bob can tell it to do whatever it is he wants to tell it to do. So the first thing Bob might tell this application to do is, please read the data off the file system, and then just send it to me in an email or some sort of TCP connection. Well, unfortunately, this is not going to work very well because the underlying system, the kernel, will not allow the web app to send a message to the network if its label is not empty. And in this case, the web application had to have A in its label to read the file off the file system in the first place. And therefore, it prevents it from sending data directly out to the network. OK, that didn't work. Let's try something else. So the web application will, at Bob's behest, do something like launch this helper application. And then the web application sends the data to the helper. And the helper, because it needs to receive data, has to have A in its label. And let's say the helper then tries to send data back to Bob. Well, of course, it's in the same position as the original web application was. And as such, it can't send data back out through, through an internet connection. Well, maybe it tries to enlist the gateway process and says, gateway, you send this data to Bob. But the gateway has this very simple rule encoded in it. It just knows what's the label of the person sending me the information, in this case, A. And it just knows not to send data labeled as A to anywhere else but to Alice's browser. And so it'll then reject Bob's request and not send that data back out to Bob's browser. Yes?
So it's not clear, how does a process get declassification privileges?
It gets only by allocating new tags. So in this case, when Bob signed up to the website, he asked the gateway asked the kernel to create a new tag that corresponds to Bob.
So gateways are the only things that can allocate these tags?
Well, any process can allocate new tags. So for instance, the web application can allocate a new tag too, but it'll just be unrelated to A and B. So the gateway is the one who's in charge of implementing the policy for this website. So it has these new tags, A and B for Alice, B for Bob. Therefore, what I haven't shown on the slide is whenever people upload data, it'll launch the web application, in this case with A already in it. So that way the web application can only write data to files labeled as Alice's data in that sense. So the gateway is the only one who knows what A and B. It's the only one actually imposing this A and B policy on the rest of the system. And therefore, it also has the ability to do the opposite, to take it off to get the information back out. So the rule is if you create a tag, you get to eventually declassify information for that tag. Any other questions? Oh, yes?
I have another question. So did the gateway in the first place save Alice's data? Because if the web app saves the data, then Bob could tell the web app, next time you see data from a new user, use my tag instead of their tag.
Yeah, that's a great point. The way that's prevented is the gateway is the one who actually launches the web application in the first place. And so when Alice's data is coming in, the gateway will launch the web application with Alice's secrecy label already in it. So in this case, even if buggy, the web application could add additional tags, but it can't get rid of that tag A. So in this case, it's forced to write files with A already in it. And the gateway is the one who enforced that policy. What I've described here at a high level is a system in which we really shouldn't have to worry at all about, and we're not worrying at all about what's going on inside the black box, that the important security policies are all being provided by the gateway, and in some sense the kernel. So this is more or less the high-level argument that we've actually factored out some of these security assumptions in our web application. Of course, this idea of information flow control is not new even in the context of operating systems. It's been around since the 80s and 70s. And so you can look at systems like Bell LiPadula or Kikos or Orange Book, IX, et cetera. And our system differs from that along mainly the second bullet point, in which we're giving applications like the gateway the ability to legislate their own security policies. So in this case, the kernel doesn't really have to know what Alice's browser is, what Bob's browser is. It's actually an application level idea. And that actually corresponds very well to building real applications in this model. So we found that this was really what it took to bring this type of technology that's been around for a while and make it practical for the case of web application development. The next thing I'd like to talk about is, given this model I described, what interface should one expose to developers to get them to actually build to allow them to build interesting applications with it? And if you sat down to do this, potentially the approach might be something like this. To start out with an existing API, one like Unix, that gives a lot of very useful abstractions, things like the open file abstraction, or reliable inter-process communication. And then on top of that, add DIFC labels and rules. The problem with this approach, though, is it turns out to be quite tricky, and there's been potentially less than perfect implementations in the past that go along that goes along these lines. So let's see about what some of the difficulties are, to be more specific. So here's a case that shows up in practice. The gateway is, in some sense, doing three things at once. It's talking to the web application to get information about Alice's request back out to Alice's browser. It's talking to the network, and in some sense, the network can be thought of as having an empty secrecy label, and therefore, to send to it, one needs to have an empty secrecy label as well. And the gateway is also doing things like authenticating Alice and Bob when they come into the service. So in this case, the gateway is talking to three separate resources, potentially in three separate threads, and all these resources have different labels. So in this case, the password database is protected by some new tag D that's not related to Alice's tag A. So the question then is, what secrecy label should the gateway actually be running as? It's not entirely clear. And another thing that comes up in practice is that it's very difficult to write applications like the gateway that have hard to find bugs in it. And so here's an example of a bug that shows up a lot in practice. Now imagine the gateway is having quite a successful conversation with its friend, the web application. And they're both communicating about Alice's data, so they both have A in their secrecy labels. And now the gateway does something interesting, like trying to access a top secret file labeled with some other tag T. And notice it doesn't have the ability to declassify that file. Well, the first thing it would do to access the file would first change its label to have T in it. And the kernel will allow it to do that and then allow the gateway to actually read that information to its address space. But when the gateway goes back to its friend, the web application, maybe a couple minutes later, it'll say, oh, wow, it disappeared. I don't know what happened to it. And maybe the web app is just taking a while to respond, or maybe it crashed. In fact, the gateway can't really know what happened to the web application here. By accessing that file, the gateway has really broken off this nice bidirectional communication that it had to the web application. So these are types of subtle mistakes that come up in practice, for which it seems like there really should be some interface that the operating system is giving to applications to help them better manage their resources. So in our system, here's what we came up with. We came up with a level of indirection to put between, on the one hand, DIFC label mechanism, on the other hand, Unix primitives. And these are just called, in our system, endpoints. What endpoints do is they allow things like the gateway to individually put labels on the different resources they're using. So in this case, this gateway has three different resources. It has a pipe going to the web app. It has a file descriptor going to the password database. And it has some sort of socket going to this network application. And it's just able to say, when speaking to each of these resources, use these different labels. So in this case, use the label A when speaking to the web application. And so this seems like an easy enough idea, but the question is, what are the security implications of this type of new mechanism? And so the first thing that we said is what should really happen is that when deciding whether to allow the web app to speak to the gateway, the kernel should actually check the labels on the different endpoints that correspond to the communication path between them and see if they meet the subset rule now. So in this case, because the endpoint label on both are subsets of the other, it makes sense for the kernel to allow bidirectional communication between these two different applications across this pipe right here. But if you think about it, what's really going on here is some sort of declassification. And that is, data is coming from the web application that has Alice's secret data, so with secrecy A. But the gateway in this picture is allowed to keep its empty secrecy label. So therefore, the gateway has to have the ability to declassify this information A. Otherwise, the kernel would be allowing some sort of information leak that we actually wouldn't want to happen in the system. So we could say there's a pretty high-level restriction that has to be made between a process's label and the different endpoints labels that a process puts on its resources. So what that should be is what we described in the slide here. And that is if there are any tags that's in a process's label and not in an endpoint label that the process owns, well, then the process has to have the ability to declassify for those particular tags. And this is useful for two reasons. First, it allows the operating system to make sure that the application isn't using endpoints to leak information. But it also allows the application to help itself to implement the right policies and therefore to prevent bugs. So here's an example as to why that might be useful. So let's say this gateway application set up endpoints so it could speak to its friend the web application using the tag A for Alice. And then it had this, what turned out to be a stupid idea, to actually read this top secret file. Well, when the gateway decided to actually add T to its secrecy label to actually read that file, what the kernel is going to tell is that, no, you can't actually make that label change. If I were to allow that, it would actually invalidate the endpoint invariant on your endpoint. And therefore, I'm going to reject that, that particular system call for the gateway to change its label. So really what this is doing is it's allowing the kernel to tell a gateway, you could either talk to the web application or read the file, but you can't do both at the same time. And this actually corresponds very naturally to what the gateway would actually want to do. And the last point I'll make here is that this level of indirection has not introduced any new axioms into our security assumptions. That the axioms are really what I described in the first part of the talk. And so if the kernel is able to enforce communication between different endpoints by checking the labels on those endpoints, and the kernel is also enforcing the fact that every endpoint on the system has to be valid in terms of that declassification rule, then what happens is that the process level rules I described early on in the talk are being upheld, and that there's really no additional assumptions we've had to make. OK, so I described to you the basic model in some detail as to what type of API we're actually using to build applications. The last questions remaining about getting OS support for information flow control is how to actually implement it. And instead of building the OS from scratch, as I implied we did earlier, we actually took a slightly different path. And we started out with something, in this case, a web application, linking against a standard version of the C library. But we, at runtime, switch out the standard C library for a new version of the C library called the Flume library. And Flume's the name of our system. And so now when this web application does something like try to open a file, this library is going to forward that system call request to this user-level process, in this case, what's called the Flume reference monitor, which is going to be in charge of implementing all the different types of security policies that I've been talking about to date. And then once the reference monitor has received that request from the application, it's then going to issue the system call. And there's one additional piece of complication here, and that is there's a very small, let's say 600-line long kernel module, which actually prevents things like the web applications from making system calls directly, but allows the Flume reference monitor to do it on the process's behalf. So that's the one piece of kernel code we've actually had to implement here. And it turns out this is a very flexible implementation technique that it works on Linux 2.6 in our implementation and also OpenBSD 3.9, which leads us to believe that it actually could work on lots of different operating systems as well. So this is more or less trying to factor out the important security decisions and putting them in user space as much as possible. And it turns out that endpoints were very useful in this implementation exercise, that we use them for things like file descriptors, but also other communication paths between different processes on our system. Things like sending signals and receiving signals, parents waiting and child's exiting, network, system 5 IPC, et cetera. And I know you probably heard a lot about information flow control this week and wondering where we fit into the picture. More or less, what we really care about in this work and what I've described today is a layer on top of the operating system. So if HiStar turns out to be the OS of choice in a couple of years, we could certainly port our types of high-level abstractions to HiStar or potentially to the asbestos operating system that I was a part of a couple of years ago. And really what we care about is A, the interface to put on top of that, and B, the type of applications you could build with it. Things like what I'm just about to describe, like a wiki in our work, or maybe things like online banking in the future. So we're really more or less in the middle of the software stack here. So I hinted at it, but the next question to look at is what are the security improvements using this type of system in a real website? And instead of building a website from scratch, we tried to get ourselves in the position of what real developers are doing today. So what we did is we took an example, an off-the-shelf web application called the Moin Moin Wiki, one which is currently in operation on a bunch of different websites around the internet, and one that also does some interesting things, like it supports third-party plugins. So we looked at this off-the-shelf application to see how we can get it to work within our framework. And here's why this is an interesting application. If you look at this, which is sometimes being used in a corporate setting, It's doing things like implementing access control policies. So here's our fake corporation that we'll be using as an example. There's some sort of manager, Alice, who has a secret file called Alice's data. There's the HR group, which is in charge of potentially laying people off in the next week, and that's Alice and another person who are able to look at this file, which Bob can't read. And finally, there are some files that all three people can read. So a very basic access control policy that people using Moin-Moin-Wiki are actually trusting the Python code in Moin-Moin-Wiki to get correct. And so as we think about securing Moin-Moin-Wiki, we're going to have a slightly different trust model from what you might be thinking. So in this diagram, the stuff in red is the things that we're assuming are secured, things that we think we got right, which include the Linux kernel and compiler and the Flume system and a whole bunch of things. And the stuff that could be vulnerable is something like the Moin-Moin-Wiki itself and the Python interpreter running it and maybe some plugins. So this might seem like a ridiculous idea if you scale this hamburger diagram in your head by the lines of code. And you'd see more or less that Linux really wins out here and our little wiki application is somewhere in the noise. But there's another way to look at it, and that, fine, Linux is a pretty big piece of code, but it's also shared amongst many different websites today. If there's ever a bug in Linux, it's pretty fast to get a patch for it and to figure out and to steal your system from that bug actually afflicting you. That's not the case for things like smaller web apps like Moin-Moin-Wiki or things like plugins. If you were to take that same diagram and scale it maybe by the lines of code divided by the number of people actually using it, you'll come up with something that looks a lot more like this, in which case the plugins in Moin-Moin-Wiki really are accounting for a lot of your vulnerability that you might be having if you run this system. And by the way, those popular press mentions of websites being broken into really all fit into this area of application-level bugs that got website operators into trouble. So here's our implementation strategy for this system. We're going to take the old picture that I've been showing you throughout and just stick Python, Moin-Moin-Wiki, and its plugins where the web application was, and put the web server and the gateway, and the gateway we've actually written specifically for this application where the gateway was. And so what that means is that when Alice comes to this website to use our new version of Moin-Moin-Wiki, she'll have her request first go through a web server, which will then fork a little gateway process we wrote, which will then fork Moin-Moin-Wiki, which will then do the job she wants. And in terms of our earlier picture, the gateway has the ability to declassify Alice and Bob's data and therefore is trusted. And the Python application doesn't really have any privileges and therefore is untrusted. So what are the results of this type of exploration? The first thing we asked is, can our Flume system that I described actually accommodate non-expert code? And the way to measure that was to think about an application we ported the Moin-Moin-Wiki and how much code actually had to change to get that correct. So in this case, we changed about 1,000 out of the 90,000 lines of Moin-Moin, but left more or less everything unmodified. What's the performance of this type of implementation? We actually did incur some overhead by running this stuff at user space in some sense. We were about 43% lower on an experiment where we just pounded this thing with read requests. But it turned out that we actually were able to show in our experiments that if we took a linear number of servers and put them into a rack together, then they would actually scale, the performance would scale nicely with the amount of machines we threw at the problem. So there is some hope for getting this fast if you really care about that. Of course, the real question to ask is what are the security improvements of this type of architecture? Yeah?
On the scalability issues, how does it scale with number of users or number of these tags you're trying to track and match against?
Tag operations are all of one. So we didn't see, well, we basically saw no real, in our experiments, we saw no effect, the number of users we were talking about with the performance of the system. And that's involved some aspects of how we implemented it, but there's nothing about these subset operations that actually don't scale with the number of users using the system. That an average label has about 1 or 2 tags in it, and certainly doesn't scale with the, and certainly doesn't increase with the number of users. Now, what doesn't seem obvious about that description was the declassification label, which actually has Alice, Bob, and Charlie, and Doug. And really, there's a level of indirection I didn't describe in which we have Processes can own one capability that corresponds to owning a whole group of other things. And we actually only have to query that group structure in the easy direction to query it. So it turns out that doesn't really make a difference in terms of scalability. But I could describe that a little bit more to you offline. It'll be a little bit more hairy details involved. So the first security improvement we saw is that we said the gateway had to be correct and the wiki didn't have to be. But the gateway is only 1/90th the size, or the declassifier is only 1/90th the size of the application. So that was a good improvement right there. But to be a little bit more precise, we actually did find in the code that we had used to implement this system, we actually inherited 2 ACL bypass vulnerabilities from the original developers. We found this out about 6 or 7 months after we had built this system. And here's one of the bugs that was in the bug databases that we saw. So you could actually type into wiki, show me the month calendar for the month of March in 2008, and call it corporate events. And wiki will then generate you as a user this type of nice looking calendar. And then you could actually click on these different links and say what's going to happen on a given day. It turns out if you mouse over what happens on a day like the 22nd, without having to log in, wiki is more than happy to tell you exactly what's going to happen that day. So in this case, it's willing to tell Bob that he's going to be laid off even though he shouldn't have seen that information. And we said, oh, this is a bug in Moin. What happens if we run an R version of Moin that didn't even change, that didn't know this bug existed? And we got something that looked like this. And when we went back, we were actually able to, once we knew the bug was there, we were able to make it much nicer for the user experience. But it was interesting, we had solved the bug without actually knowing it existed in the first place. And the same type of argument held for the 2 or 3 other bugs that we found against wiki. So something interesting to keep in mind here is that, of course, there are lots of really good bug-stopping techniques out there, things like taint tracking or software fault isolation. There are a whole bunch I mentioned here. These are great techniques, but it's unclear they would have helped at all in finding these ACL vulnerabilities we saw in Moin. And the reason, yes?
I'm just a little confused because there is, you have no longer revealed, mass layoffs, but traditionally in information flow, there are bits coming out, right? You got an HTTP error on the 22nd, but not on the 21st, right? So if I'm trying to decide when to sell my stock in the company, I can still know that something big is going to happen on Saturday.
Sorry, I did not describe it entirely accurately. You get error 500 when it even shows you that page in the first place. So it wouldn't even get to it. As long as you set it up so that there's a more secret page referenced by a public page, the calendar wouldn't even render in our example. But the interesting thing about this bug is that Python is doing exactly what it should be doing. It's not executing any third-party x86 code in an overrun buffer. The problem, though, is that Python just wasn't doing the right thing. And that's why to solve this issue, you really do need something like the system we've described. OK, so the last thing I want to do is try to generalize the results I've shown you up to now and see how it might work against things like, might work in the case of new web applications that we're going to build in the future. And we're calling this platform W5. And here's the insight that we had. Here's a picture of the Flume wiki as I described it before. What was different about our system is that we put all security guarantees into the gateway and treated the wiki itself as a black box in terms of security. So what happens if we replace that black box with third-party code that's unvetted, suspect, uploaded by our worst enemies? And our idea here is we could maybe get the same types of security guarantees out of the system. And so this brings into proposal a new type of architecture. We're calling this architecture W5, in which some service provider sets up an operating system using Flume, sets up some sort of gateway, but invites all sorts of third-party developers to take their best software and to upload it onto this server somewhere in the middle of the internet. And applications can then operate over Alice and Bob's data, subject to the security policies being enforced by the gateway. And there are a bunch of different things to think about in this architecture. But one of the more interesting is, you might be asking, how can people actually share data? And so, of course, somebody like Alice might want to share her photos with Chuck. How is that? Can we accommodate that decision? Well, here's an example about how that might work. Alice's photo is labeled with A for Alice. And some photo sharing application, when it reads Alice's data, is going to actually have that tag A on it as well. But instead of sending the data back out to Chuck's browser, it then routes it through this thing called a declassifier, which Alice has uploaded onto the server or authorized to run on her behalf. And you know it's authorized to run as Alice because it has the ability to declassify Alice's data. What it'll do is it'll know that Chuck and Alice are friends, so it'll be willing to strip off the tag A and apply the tag C to that data, and then allow it to send out to the internet. So in this case, Chuck can then see Alice's photograph. Yes?
And how can you keep Bob out from doing the same declassifying?
Well, because the declassifier knows that Bob and Alice aren't friends, so it'll know never to pull off A and put on B. It'll say, only pull off A if you put on C, or if she's friends with Frank, to put on F instead. Yes?
Do you have a system where Alice's declassifier can only access sort of certain parts of Alice's data and not others? Or would that have to be done in something that's not related to the tagging system?
It seems like that could work. I don't see why that couldn't. But this is just a proposal at this point. But my guess is yes, it could work. Yes?
So one of the advantages of the system prior to this is that the gateway sort of handles this sort of security management independent of what Alice wants to do. But this seems to open a phishing attack where if Bob can trick Alice into loading a declassifier for him,
Right.
everything's exposed to Bob.
Sure. So you said a phishing attack?
Yeah, I mean, I'm not sure what
All right, I agree that there are certainly some user interface issues here where Alice has to make sure not to give her password away to people, and she has to know.
Password, I mean,
So you're talking about how to provision these declassifiers.
right. The fact that Alice can inject a declassifier for a friend, doesn't that open the attack to injecting a declassifier for somebody other than who you expect?
Well, so what I described is there's most likely going to be some interface in which Alice logs on to the system and some web page generated by the application, by the platform provider will say, Alice, here are the 4 declassifiers you can use. You can use Max's or Microsoft's or Adobe's, and click here to authorize that declassifier to work for you. I mean, that's the type of interface we're describing, where we're envisioning, where some trusted party needs to actually implement that interface correctly. And that's what allows something like the classifier to be provisioned with Alice's declassification privileges. Otherwise, yeah, I mean, you're right. We exactly have to make sure that's not an issue. I mean, the important thing about this architecture, though, is that the declassifier doesn't care at all about what the data is. It's opaque data, so it works the same on photographs as it does on blog posts as it does on financial records. What really matters is what the label is on the data. And that's the type of factorization we can get in the system that's hard to get outside of an information flow control system. And just to slowly wrap up, what's trusted in the system, and I think we're kind of getting at that with these different questions, are these pieces that I've shown on the slide here. That the platform has to be trusted, the gateway, and also some type of declassifier that Alice is going to use to share her data with friends. But what isn't trusted are all the different types of applications that we could put where the photo sharing application was. And so this is what people are using with Facebook applications now. All these things can fit on the right-hand side of the slide. So I've been doing this interview process long enough to know that many people are bound to ask me, what am I doing next? The first is what I'm currently doing right now, which is evangelizing the system, because I think it's an interesting way to build applications. And this requires an interview and is currently in progress. But assuming that there's a job in the future, the idea next is to build out this system. And there's a lot of things we need to do to get this right. I just hinted at a couple of them, but we need to spell out the appropriate policies. You have to think about how SQL is going to work in this new world. The browser and JavaScript need to change. There are many, many things that are very interesting problems that exist if you think this is the right way to build web applications. So just to conclude, we had a high-level idea that we talked about throughout the talk, which was that of end-to-end website security, factoring out as much as possible the code of a system into untrusted parts and parts that had to be secure. To realize this, we had to more or less think about the way the operating system was being implemented. And we had to, for it, make a new model, which we call Decentralized Information Flow Control, and think a lot about what it takes to write applications. We introduced a new primitive called Endpoints, and also described how to implement it for standard operating system abstractions and to implement something like MoiMoinWiki on this type of platform. And in the future, we think the way to go with this is to try to build these new interesting web applications built on these types of information flow tracking primitives in order to get something like Facebook, but to be much more secure and to give people real useful systems with good security guarantees. The last thing I'll mention is that this is open source software, so you can download and play around with it if you like. It works more or less on your Linux machine without much, without interacting negatively with the things you already need it to do, so it's pretty non-intrusive that way.
So it strikes me that there's sort of two classes of bugs, security vulnerabilities in systems, right? Or at least for web applications. There's authentication problems and there's authorization problems. I mean, it looks like this system essentially eliminates authorization problems. But as far as authentication problems go, is essentially the way that the system is hardened against them by concentrating the authentication sort of like system into the gateway, or is there another way that it takes care of it?
The question was, how do we deal with authorization bugs?
Authentication.
Authentication bugs? I believe this isn't something we really focus too much on. We say that you could use web certificates or just username and passwords for users to authenticate themselves to the gateway. If browsers are not authenticated, then they can't get any information out. And so basically what that authentication does is that makes the process on the other side, on the gateway process running on the server, it allows that process to get declassification rights out of the operating system, out of the kernel. And so without those, no process can get Alice's or Bob's secret data out to the browser. So that's, as far as I know, the best way to answer the question. Something I didn't talk about at all, by the way, is how to prevent malicious applications from overwriting data, from corrupting or overwriting good data. And that's entirely an orthogonal mechanism, integrity, that we describe in the paper. So I don't know if that is at all related to your question, but yeah. Yes?
So I'm trying to think about, so Facebook has a lot of these types of things built in already. Users can specify security levels for information.
Right.
Users can sort of specify what applications can touch what kind of information. And as far as I can tell, none of those controls mean anything to users, and they don't work, and they never fit with what users want to do. So it seems like there's a lot of challenges in that direction, and I want to know what your thoughts are on how we can get anywhere near there.
So I agree that we have not solved any HCI issues or we have not made the issue of what problems to tell the user. We haven't addressed those. Well, I think we have addressed one of the issues you did mention, though, which is that the user on Facebook says, I'm going to use this new poker application. And Facebook will say, this is written by Corporation Y. Is it OK to let Corporation Y access my data? That is a terrible decision to give the users, because users have no idea. They say, yes, do my work, but they have no idea what the code is, what Corporation Y is. I mean, they're not compilers, and even compilers might not be able to tell you. So what we've allowed in the system, as I've described, is a way to allow users to experiment with applications without having them worry about stealing their data. I think the interesting thing about Facebook saying, you allow this application to view my data is the same problem that we have on our desktops when we say, allow this iTunes application to be installed in my system. I mean, users have no way of answering it. So what we do is we give in our system the ability to have this lazy check, to run the code and to let the code access the data, but not to expose the data unless it meets another security policy. So I think that's really the key difference between what we described and what's already there. The other key difference is that exists, and this is more or less a proposal.